Okay, so let's have a look at the demo of the transport network optimization in the city of York. York is a fascinating case study. It's a walled city with significant historical infrastructure, including city walls, 2 rivers, and numerous bridges, especially concentrated in the city center. The modal split shows that approximately 60% of the trips are made by car. These geographical and historical constraints make space extremely limited. Combined with the high car modal share, York presents unique challenges for transport planning. The goal of the work I'm presenting today is to validate some of the MOs in the context of the city of York. In this work, we validated 6 MOs modules. The validation is structured into 2 main parts: a real-time component that you can see at the top of the slide, and an offline component that you see at the bottom of the slide. In terms of input data, we used GPS data from cars and a static map of the city. This input data is feeding the real-time component of this work, which includes the extreme scale FCD analysis that is integrated into PTV Flow's product, the traffic monitoring and visualization tool. The same GPS and map data are also used in the offline component, which include trajectory data analysis, travel time analysis, which also uses GTFS data, but also CMOLD extreme scale map matching, which output is fed into the hotspot analysis. And then at the bottom right hand side, CMOLs are fed by the output from the real-time FCD analysis, so specifically the speed on links. And these MOLs are highway congestion prediction and public transport-based traffic estimation, which actually uses GTFS data as primary input. The GTFS data are from public buses in York. In the next part of the presentation, I'll walk you through each of these modules step by step, showing how they contribute to a comprehensive understanding of York's transport network. Let's start by looking at the input data used in this study. The data covers the period from 22nd of July to 12th August 2025, which coincides with the summer holidays, a particularly challenging time for traffic analysis due to atypical travel patterns. For GPS data, we acquired a commercial dataset containing device ID, longitude and latitude, and a timestamp. We compared this data with traffic counts from the city of York and found that it represents approximately 0.4 to 1.2% of the actual traffic volume. This relatively low coverage adds an additional layer of complexity to the validation process. For public transport, we used real-time GTFS data for buses. This data is available through the Bus Open Data service provided by the UK government. When you see speed on links as input, this is the output of the real-time extreme scale FCD analysis, MOLD, and for the static map, we used OpenStreetMap data. Now let's take a closer look at the real-time component of the work. In this part, we use the MOLD real-time extreme scale floating car data analysis. The module performs a real-time map matching of GPS data to a static map, trajectory reconstruction, and speed estimation on network links. This enables near instantaneous insights into traffic conditions across the network. The real-time FCD module requires a static map, device ID, timestamp, and coordinates, so the GPS data is ingested as a real-time data stream, while the map is loaded as a static input. This MOLS module has been integrated into PTV Flows, a commercial product from PTV. PTV Flows is a traffic and mobility monitoring tool offering real-time traffic visualization, estimation and prediction services, machine learning-based forecast, alerting mechanism, and KPI dashboards. In the current commercial version of PTV flows, the map and speed data are sourced from commercial providers, which can be costly for clients. In our emerald-based version, we replace the commercial map with OpenStreetMap data, and we also replace the commercial speed data with GPS data. This approach offers greater flexibility and cost efficiency for clients, allowing them to choose more affordable data sources. Okay, so let's now have a look at the demo of PTV flows. So when you open the software, there is a short loading time while the data initializes. And once loaded, you can view the data for the entire North Yorkshire region. You see some bold lines indicating corridors with defined KPIs that has been set by the City of York itself. And you see real-time speed in miles per hour. And going on the corridor, now you can see travel time indicators that are color-coded with alerts for abnormal values or congestion. One can click on the corridors and see the current travel time, which here is 18 minutes, and the free flow travel time, which here is 9 minutes. We can go on the second red corridor and see that the current value is 3 minutes instead of 1. Then we can open a graph view showing expected travel time over time and also travel time trends, helping to identify patterns or anomalies. Going back to the map, closing everything, one can zoom out and access the forecast data for the next 0, 10, 20, 30, 40, 50, and 60 minutes. So here I click on 60 minutes. The map colors did not change significantly, indicating that no major traffic changes are expected in the next hour. Additionally, you can inspect forecasted speed and forecasted travel time on the specific corridors of the map. Now let's move to the offline part of the work. This component has been fully integrated into QGIS, an open source geographic information system software. We begin with the trajectory data travel time analysis using a tool called TrajecTool. TrajecTool is a no-code plugin available in QGIS, which is designed for quick and flexible analysis of floating car data and public transport data. It's ideal for initial exploration and visualization of mobility patterns. It needs as input raw GPS data or GTFS data for public transport, and the outputs are trajectories. There is also a toolkit for data analytics. Okay, so for the demo, we start by looking at GTFS data. You can see here bus lines and stop locations. Now trajectory points that are color-coded based on frequency, and also stop points that are also visible with longer stops indicated by larger symbols. This helps identify frequent stopping areas and stop near intersection or high traffic zones. We examine FCD data for the same intersection. You can see the car trajectories with color indicating how often each point is counted, and you see the stop points that are visible next to intersection and public transport stop. This allows us to compare car and bus behavior in the same area and also potential congestion or interaction zone. To go deeper, we analyze the normalized speed distribution on one of the streets. This is done for different times of the day, helping us understand the speed variability, time-dependent traffic patterns, or also potential bottlenecks. The next step in the offline workflow is the extreme scale map matching and hotspot analysis modes. The map matching module aligns raw GPS data with the road network to generate more accurate vehicle path representations. The process uses the Valhalla routing engine to match GPS points to the correct road segments. This improves the spatial accuracy of the data, especially around intersections and complex road layouts. As inputs, it takes a static map, device ID, timestamp, coordinates, and these inputs are fed into the MOLs for map matching. As outputs, we get corrected coordinates, estimated speeds, and heading direction. On the left-hand side, you see the original GPS points, which are often misaligned with the road network. After map matching, the points are accurately placed on the road segment. And finally, on the right-hand side, you can see the refined trajectories, especially around intersection where precision is critical. So you can see that there are even more points than before. And this can be used for different applications, and one of them is the hotspot analysis. This module identifies statistically significant areas of high traffic concentration. The analysis is based on the JETIS or GI star statistic, which helps to detect spatial clusters of high activity. It takes as input a static map and correlated coordinate from the map matching module, and as output, it gives the concentration zones map onto road network segments and the identification of potential congestion hotspots. Animation, you can see the hotspot depending on the time of the day. So we have nothing during the night and it's varying during the day. Now we jump into the highway congestion prediction that takes speeds on links as an input. Anticipating traffic jams is critical for urban mobility. Congestion leads to increased fuel consumption, higher emissions, and elevated safety risk. The highway congestion prediction module uses a machine learning-based approach that combines multi-scale temporal lags and directional spatial lags, and the model is built using LightGBM and XGBoost that are algorithms that allow for scalable and interpretable deployment. Importantly, the approach avoids reliance on historical maps or graph-based simulation, making it more flexible and adaptive. Accurate forecasting enables proactive traffic management, smarter urban planning, and real-time adaptive control. CMOs take speed on links as input that are provided by the real-time FCD analysis MWorld, and as output we get forecasted probability of congestion on each link. This allows traffic managers to anticipate and respond to congestion before it occurs. So here what we see is the F1 score of the congestion prediction. The darker the better. And now in red, those are the important features. This is also an output of the model. And these features correspond to specific temporal or spatial information. They allow the model to capture complex traffic patterns, enabling it to generate more accurate, context-aware predictions and provide deeper insight into the factors driving congestion. Finally, the last MOL, public transport-based road traffic estimation. So this module leverages bus data as moving probes to estimate traffic conditions for private vehicles. The model uses a deep spatio-temporal convolutional network to map bus speeds to generate traffic speeds. So this enables us to use readily available public transport data, estimate segment-level average traffic speed, and reduce reliance on expensive or proprietary car data. The module takes as input the speed on links from GTFS bus data, also the speed on links from car GPS data, but only for reference, and a static map. So those are fed into the MOLs module, and as output we get the estimated car traffic speed on road segments. Here you can see the estimated car speeds along a corridor in York from the city center to the highway. And depending on the time of the day, most speeds range from 8 to 14 miles per hour, which corresponds to roughly 12 to 22 km per hour. And this demonstrates the model's ability to reflect realistic traffic conditions using only bus data. So in conclusion, we successfully validated 6 AMOL modules in the context of the city of York, despite the challenges such as limited data coverage and a short study period of 3 weeks during summer holidays. The models performed well. They enabled visualization and analysis of real-time and offline data. If you are interested in more details, check deliverable 5.8, AMOL toolset adoption, and lessons learned.